Something that you might suspect about bases is that if you have a vector space, every basis should have the same size. Well, that's a good idea to check, but it's a little hard to talk about size if your bases are infinitely large. So let's concentrate our attention on the case where our bases have finitely many entries, or finitely many vectors in them. So how could we compare the sizes of two bases? So right, if we have some big list of vectors in one basis and a big list of vectors in another basis, right? We don't know at the beginning if it's actually the same size, so I have to use use a different ending subscript. It's a little bit hard to know how to go about comparing these two bases, but we can simplify this a little bit if we think just about replacing elements in B one by one. So rather than comparing these two collections all at once, what we're going to do is first replace B1 with C1 and see how that compares with B. And then replace B2 with C2 and see how that compares with B. And since there are only finitely many vectors in B, eventually we'll be done with this replacement process, and then we'll have a comparison of B with C. So the point of all of this is we're going to do this step by step. So rather than jumping to comparing these two bases directly, let's see what happens if we replace just a single vector in a basis. So to give a little structure to that process, let's suppose that we have a vector space V and a basis for this vector space B, which is beta 1 through beta n, so it's a finite basis. And let's suppose we have a vector in V that is a that we can write as a linear combination of the basis vectors in this way. So C1 B1, C1 beta 1 up through Cn beta n. So these C's are scalars, right? These are just constants. And let's suppose that the ith scalar multiple C is not 0. Then we can replace the beta in position I, which in general is going to be in the middle of the list somewhere. Then we can replace the beta sub I with V in this basis, and we'll get another basis for our vector space. So, right, what we're saying here is we can replace a beta with V as long as the corresponding coefficient isn't 0. All right. So, if we do that, what we get is a new collection of vectors that I'm going to call B hat, which is beta 1 up through. So, right, beta I would be in this ith position, but we're going to replace that with V. So right before that is beta sub I minus 1, and then right after that is beta sub I plus 1, okay, all the way up to beta sub n. Of course, if I is equal to n, then actually V is at the end of the list, but you get the idea. All right, so what we want to do now is show that this collection, beta hat, is a basis for V, right? That's what we're trying to show. We want to show that replacing beta sub I with V gives us a basis for capital V. All right, well, we need to show that this spans capital V and also is linearly independent. So let's do linear independence first. So let's suppose that we have a linear combination of these things that a linear combination of these vectors in beta hat that gives us 0. So in other words, suppose we have a linear dependence relation, right? That's what I'm really saying. So what would that look like? That would look like A1 beta 1 plus so on up to A sub I minus 1 beta sub I minus 1. And then the next vector in our list is V, so A sub I V, right, because we've replaced beta I with V, plus A sub I minus 1, or I plus 1, V beta sub I plus 1, there we go, all the way up to A sub n V sub n. All right, and we're since we're assuming we have a linear dependence relationship, so that means this we have some linear combination of these things adds up to 0, the 0 vector in capital V. All right, so what are we trying to show? We're trying to show that all of these a's are equal to 0, and really the only headway we can, I mean the only option we have, the only thing we can do is use what we know about V. What do we know about V? Well, we know that V is given by this linear combination of the betas. So we can rewrite the right-hand side, a1 beta 1 plus dot dot dot, down to ai minus 1 beta I minus 1 plus a sub I times, and then replace V with this thing. So c1 beta 1 plus dot 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 down to cn beta n. All right, so that's just this, this mess here corresponds to the V term in the line before. And then plus ai plus 1 beta I plus 1 plus dot 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 down to a sub n b sub beta sub n. This should be a beta right here, not a V. Okay. So what next? Well, I mean, look, we have in these parentheses we have a bunch of terms that have betas in them. So why don't we group terms that have the same beta? Okay, so on the left-hand side it's still the 0 vector. On the right-hand side we have two beta 1 terms, right? There's one here and there's one there. So putting those together and factoring out the beta 1, we get a1 plus aic1 beta 1 plus dot dot dot, right? We get the same thing all the way down to the beta sub I minus 1 term. So that's a sub I minus 1. And then in here somewhere there's a beta sub I minus 1 term, which looks like ai times c sub I minus 1, all times beta I minus 1. And then in this sum here, hiding inside of the dot dot dot, there is a beta I term, right? So the next term is a sub I, c sub I, beta sub I. And then the rest of the terms, come from the rest of the betas. They look a lot like these first ones. So plus a sub I plus 1 plus a sub I c sub I plus 1 times beta sub I plus 1 plus dot 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 down to the end, which is going to be a sub n plus a sub I c sub n beta sub n. All right. Incidentally, this kind of proof where we have to write out all of these terms, keeping track of all of the indices is kind of annoying. I think it's more important just to keep track of the general pattern of what is happening for each term, right? We have lots of different terms, but they only come in two types. There are the types for the betas that we aren't replacing, and all of these terms look the same, just with different subscripts. And then there's the term coming from the beta that we replaced. So, there are lots of terms, but they only come in two types, so it's not that bad. All right. So now what, right? We have this big mess equal to 0. Well, look, all of the betas, beta 1 through beta n, are linearly independent. We know that because they form a basis, right? So they have to be linearly independent. So here we have a linear dependence relationship among linearly independent vectors. That means the coefficients have to all be 0. So a sub 1 plus a sub I c sub 1 has to be equal to 0. And so on, down to a sub I minus 1 plus a sub I c sub I minus 1 has to be 0. That's right, this coefficient. And then this coefficient, a sub I c sub I, has to be 0. And then the rest of these coefficients have to be 0. So a sub I plus 1 plus a sub I c sub I plus 1 has to be 0. And then a sub and down to a sub n plus a sub I c sub n has to be equal to 0. Okay, great. So what next, right? What does this tell us? Well, notice this equation right here. Right? We know a little bit more about this equation than all of the others because remember at the beginning we said that c sub I is not 0. Right? Just to remind you, right? I was the index where we were replacing the beta with index I, and we chose that index by saying that's that coefficient c has to be non-zero. Of course, there has to be a non-zero one because otherwise v would just be the 0 vector. Which, then we couldn't replace. And so, right, we have to have one of these coefficients that's non-zero. All right, so for this equation, we know c sub I is non-zero. So we have a product, but c sub I is a product equal to 0, but c sub I is equal to 0, or isn't equal to 0. That means that a sub I has to be equal to 0. All right. Well, now that we know that a sub I is equal to 0, look at all of the rest of these equations, right? The rest of these equations have a sub I in them. So for the rest of these, right, now that we know a sub I is equal to 0, we know that the rest of these equations actually say, let's see, this first one says a sub 1 plus, well, right, this term, a sub 1 times c sub I, is 0. So a sub 1 plus nothing. It's just a sub 1 equals 0, down to a sub I minus 1 equals 0. And then down here, a sub I plus 1 equals 0, down to a sub n equals 0. So look, what we started with was a linear dependence relationship where the a's were the coefficients. And what we just figured out is that all of the coefficients in our linear dependence relationship are 0. In other words, our linear dependence relationship is the trivial one. So the only linear dependence relationship is the trivial one. So this set, beta sub 1 down to beta sub I plus 1, v, and then this should be beta sub I minus 1, v, and then beta sub I plus 1, down to beta sub n, right? Our basis, but with the replacement, with b sub I replaced, is linearly independent. Okay, good. That's half the battle. Right. So remember what we were doing. We took this basis, we replaced beta sub I with v. We want to show that that results in a basis. We just did half of it. We now know that b hat is linearly independent. So now we need to show that b hat spans v. Okay, so how do we show that b hat spans v? Well, what we need to do is take a vector in the vector space v, any vector, right? We need to show that W is a linear combination of vectors in b hat, right? Because this will show, right, and this is just another way of saying that W is in the span of b hat. I mean, I guess I should say we know that the span of b hat is contained in v because it has to be, right? Everything in b hat is in v. So really, the only question is v contained in the span of b hat? So to show that, we're going to take a vector, any vector from v, capital V, and show that it is in the span of b hat. All right. Well, what do we know about vectors, arbitrary vectors from v? The only thing we know about arbitrary vectors from v is that they're linear combination of the basis vectors beta 1 through beta n. So we know we can write W as a linear combination of the betas. So let's say it's a sub 1 beta sub 1 plus dot 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 down to a sub. Actually, I guess I should probably write the ith entry separately. So down to a sub I minus 1 beta sub I minus 1 plus a sub I beta sub I plus a sub I plus 1 beta sub I plus 1 plus dot 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 down to a sub n beta sub n. Okay. And remember also that V is a linear combination of the betas. So V is C1 beta 1 plus dot 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 down to Cn beta n, and Ci is not equal to 0. Well, that means since Ci is not equal to 0, we can solve this equation with V in it for beta 1. If we do that, what we get is, I'm sorry, not beta 1, beta I. What we get is beta I is, right, we have to move all the other beta terms to the other side and then divide by C sub I. So we get 1 over C sub I times V minus C1 beta 1 minus, and so on, all the way down to C sub I minus 1 beta sub I minus 1, and then minus, right, skip over the beta sub I term because that's the one we're solving for, and then C sub I plus 1 beta sub I plus 1 minus, and so on, down to C sub n beta sub n. Okay, so we've solved for beta sub 1, so what we can do is just take this value for beta sub I and plug it in right here. Right? So this is going to take a lot of writing, but I'm just substituting this beta I into there. So so we get that W is equal to a sub 1 beta sub 1 plus dot 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 down to a sub I minus 1 beta sub I minus 1 plus a sub I times, so I won't even write it, it's this big mess, plus all of the rest. So a sub I plus 1 beta sub I plus 1 plus dot 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 down to a sub n beta sub n. Okay, what were we even trying to do? Remember, we were trying to show that W is in the span of beta hat, so we want to show W is a linear combination of all of the betas, but with beta I replaced by V. Well, look, we're almost there, right? We have a W expressed as a combination of all of the betas, but beta I isn't in this list because we did this substitution, but V is in this list. So just to make things explicit, right, gather up the beta 1 terms. So here's an A1 times beta 1, and right here, here's a minus C1 over Ci times beta 1. So minus C1 over Ci times beta 1. And then so on, all the terms down to the I minus 1 term look the same. So a sub I minus 1 minus C I minus 1 over Ci beta I minus 1. Okay, and then comes the V term, and the V term is just 1 over Ci times V, and then all of the terms after that. So this is going to be, let's see, a sub I plus 1 minus C sub I plus 1 over C sub I, oh, beta I plus 1, and then plus dot 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 down to a sub n minus C sub n over C sub I beta sub n, right? And of course, you see why Ci can't be 0. It's because we need to divide by it, right? Okay, so this, look, now we have W as a linear combination of all of the betas except beta I, but including V. So W is in the span of beta hat, or B hat. So the span of B hat is equal to our whole vector space V. So B hat, remember, we already know it's linearly independent, so B hat is a basis for v. Okay, finally, looking back up at what we were trying to prove, which we have proved now, right? We were trying to prove that if you have a vector that is a linear combination of your basis with one of the coefficients non-zero, you can do this exchange and you still have a basis. So what we're going to do next is use this to do a step-by-step exchange to turn one basis into another, and that's going to show that the bases have to have the same number of vectors in them.